Hello and good day. My name is Amir Arif Najimuddin, student ID 25410. Would like to present a technical review on development of Gaussian beam migration under the subject of seismic wave and imaging. The abstract for this technical review as shown on the screen. The objective of this technical review is first to study the fundamental of Gaussian beam migration. Second, to study the evolution of Gaussian beam migration algorithm. And third, to discuss and suggest on Gaussian beam migration development. We start the review by introducing the Gaussian beam migration fundamental. Standard ray methods suffer from the caustic problem caused by the non-regular behavior of the ray fields within a complex structure model. A Gaussian beam is an approximate high-frequency asymptotic solution of the wave equation in the vicinity of the central ray. The Gaussian beam approach is not characterized by singularity along the ray path, even within the realm of caustics, because it employs a complex-valued geometrical spreading. Each Gaussian beam from the sum must be taken with the amplitude defined by the source which generates the ray field. Gaussian beam migration is an alternative method to pre-stacked Kirchhoff depth migration. The resulting image lies somewhere in between the wave equation and the ray method. Utilizing Gaussian beam to stimulate the wave field is more accurate and stable, and as such, better at preserving features of the wave field. Gaussian beam superposition method is a powerful extension of the ray method. When talking about Kirchhoff pre-stack depth migration, the algorithm can be extended to deal with laterally varying structure by using standard ray path methods. But the extension can have difficulties when there is complex velocity structure, therefore resulting in good imaging of the subsurface target in addition to a certain amount of migration noise. On the other hand, Gaussian beam depth migration has no deep limitations except that the recorded energy must not graze the recording datum as the regular behavior of Gaussian beam allow extrapolation method to overcome the difficulty with caustic. Therefore, the product of algorithm can image steeply dipping reflectors and will not produce unwanted reflections from the structure in the velocity model. The procedure of Gaussian beam migration can be divided into three steps. First, decompose the seismic data into a Gaussian beam form. Second, downward continue each Gaussian beam into the subsurface. And third, obtain an image based on the imaging condition. Gaussian beam migration can be classified into two major development trends, travel time-based and wave field-based scheme. An essential element of travel time-based Gaussian beam migration is to form local plane wave gathers using a slant stack transformation of the data, which are then projected to the image domain according to the travel time relationship between the source side beam and receiver side beam. Wave field-based Gaussian beam migration is similar to migration methods based on two-way wave equation, referred to as reverse time migration. It relies on the calculation of the forward and backward propagated wave fields using Gaussian beam propagation operators. The subsurface image is obtained by calculating the coherence between the forward and backward propagated wave fields. In the case of 2D, consider scalar wave equation describe seismic wave equation as shown in equation 1, where omega is wave frequency and cap v is velocity at a point within central ray. Equation 1 is later developed into equation 2 in order to obtain Gaussian beam in high frequency limit, where S and N are ray-centered coordinates. S is the length of central ray path. N is an arbitrary reference point along the central ray path. Tau is travel time, cap v is velocity, and m is the second derivative of travel time with respect to coordinate n. Ray tracing equation is computed to obtain the central ray's travel time and trajectory as shown in equation 3. The complex valued function m can be written as shown in equation 4, where k is the Gaussian beam front curvature, and L is the Gaussian half-width beam at frequency of 1 Hz. M can also be computed based on wavefront curvature as shown in equation 5. When Q is not equal to 0, it indicates no singularity within caustic region. Therefore, Gaussian beam summation is regular everywhere along the ray path. Chervany and Shenchik mentioned two properties of Gaussian beam. Firstly, the amplitude of each beam decreases exponentially with increasing distance from the ray along the parabolic wave equation. Secondly, small minimum effective half-width of the beam resulting in narrow beam at x equal to 0 and rapidly increase in width with increasing in distance. Large minimum effective half-width of the beam, however, resulting in broad beam at x equal to 0 and slowly increases in width with, with increasing in distance. Next, we look on the evolution of Gaussian beam migration algorithm developed over the past 4 decades. Popov in 1982 proposed a new method of computing the wave field using Gaussian beam, expressed in 3 steps. First, construct a fan of rays passing through some vicinity at an arbitrary point. Second, construct the Gaussian beam for each ray of the fan. And lastly, summarize the contribution of the Gaussian beams at that point over all the rays within the fan. Giovanni and Senchik in 1983 proposed a asymptotic high-frequency solution for the computation of wave fields in two-dimensional laterally inhomogeneous media, where complete wave field is obtained as an integral superposition of all Gaussian beams arriving in some neighborhood of the receiver. In the same year, Giovanni and Senchik proposed asymptotic high-frequency solution based on elastodynamic equation in three-dimensional elastic inhomogeneous media, where parallel ray plane approximation is solved by reducing such equation into Schrödinger parabolic equation, followed by numerically solved for Riccati matrix equation and analytically solved for transport equation. Kachalov and Popov in 1988 proposed space-time Gaussian beam pre-stack depth migration method by avoiding the Fourier frequency integral, instead replacing it with the sum of residues at the poles of spectral density of a time pulse. Hill in 1990 provided the initial detailed process of Gaussian beam migration and laid the foundation of Gaussian beam migration. The migration involved decomposing the seismic data using the local slang stack without the sparse assumption. The migration initiative is to find the set of beams that will sum to produce the recorded field downward propagating, and summing this set of beams produce the distribution of energy sources. Hill in 1992 solved for the computational efficiency of Gaussian beam migration by identifying two main problems in Gaussian beam migration images. Khalifa in 1995 implement Gaussian beam migration on both isotropic and anisotropic medium to identify significant parameters differences by modifying the kinematics and dynamics in the required ray tracing. Hill in 2001 demonstrated both post-stack and pre-stack Gaussian beam migration methods in evaluating the effectiveness for structural imaging for the case of multipathing of seismic energy. Lugara et al. In 2003 developed over-complete frame-based Gaussian beam summation based on window and wavelet transform to address some of the issues related to completeness of beam summations. Gray in 2005 extend Gaussian beam migration to common short seismic data, making the migration more flexible, allow the migration of dataset with variety of azimuths, and allow a simplified treatment of near-surface issue. Gao et al. In 2006 developed a fast beam migration algorithm designed specifically to facilitate rapid migration turnarounds to allow for interactive velocity model building and validation by migrating only peak events. Zacek in 2006 developed space-time wave field with series of Gaussian packets and implemented a Gaussian packet migration algorithm by expressing the amplitude of a Gaussian packet in the form of an integral transform similar to the forward coherence state transform. Zhu et al. In 2007 reformulate the ray tracing system for anisotropic media in terms of phase velocity and extend the pre-stacked Gaussian beam depth migration to the general transversely isotropic media from that system. Popov et al. In 2007 developed the reverse time migration with Gaussian beams, thus enabling target-oriented migration and multiprocessing of huge amount of seismic data. Norwalk in 2008 proposed a focused Gaussian beam migration scheme based on strategy allowing for the narrowest portion of beam to occur at the depth of a specific target geological structure. Wu et al. In 2008 proposed a one-way wave equation-based Gaussian beam migration using local cosine beam migration method. Hu and Stoffa in 2009 developed a slowness-driven Gaussian beam migration algorithm for sparse low-field seismic reflection data by incorporating pre-stacked instantaneous slowness information into the imaging condition. Gray and Blaystein in 2009 construct two true amplitude version of Gaussian beam migration, the first of which was based on cross-correlation imaging condition and the second was based on deconvolution imaging condition. Nowak in 2011 proposed the technique of dynamically focused Gaussian beam migration characterized by the same planar beam fronts at all points in the subsurface by using the dynamic Gaussian beam initial value. Li et al. In 2011 developed a constructive algorithm to improve wave equation fidelity of Gaussian beam by solving the complex equinal equation by rewriting the complex travel time as background real and imaginary parts and their respective perturbations. Protasov and Cheverda in 2012 developed a true amplitude pre-step migration of multi-component data based on the use of elastic Gaussian beam for walkaway vertical seismic profile (VSP) acquisition system. Gang et al. In 2014 proposed two post-stack Gaussian pack depth migration method based on Gabor frame decomposition and asymptotic propagation of Gaussian packet. The first method is Dreamlet Gaussian packet method, whereas the second method is the Gabor frame Gaussian beam method. Han et al. In 2014 developed a pre-stacked Gaussian beam two-dimensional depth migration method for the converted PS wave in transversely isotropic media. Yadari in 2014 proposed true amplitude vector acoustic Gaussian beam migration upon multi-measurement seismic data based on Green's function theory, which can remove the ghost effect and produce amplitudes on reflectors that are proportional to the reflection coefficient. Protasov in 2015 revised on true amplitude Gaussian beam migration upon multi-component seismic data in two-dimensional anisotropic elastic media by identifying the global regularity of chosen weight summation Gaussian beam from the computed rapid velocity variation for a range of available deep angles. Young et al. In 2015 developed an amplitude-preserved adaptive focus beam migration which can resolve the imaging contradiction between the shallow and depth regions. Huang et al. In 2015 developed a common short Fresnel beam migration based on wave field approximation of Gaussian beam by limiting the beam's effective half-width with Fresnel zone radius to cater for complex topography. Young et al. In 2015 incorporate Gaussian packet into the reverse time Gaussian beam migration in time-space domain. Yin et al. In 2016 proposed a new forward modeling method with the space-time Gaussian beam by reconstructing the source wavelet at any given source point. Hu et al. In 2016 developed the least square migration by utilizing the Gaussian beam as the wave field extrapolating operator. Liu and Wang in 2016 implement sparse decomposition into Gaussian beam migration by solving for waveform interpolation coefficient. Yang and Zhu in 2017 incorporate data-driven optimization to solve for low signal-to-noise ratio in Gaussian beam migration by estimating the instantaneous emergence angle of specular rays using semblance analysis for local common short and common receiver gathers. Yang et al. In 2018 developed time domain bound modeling and least square migration method based on Gaussian beam summation. Liu and Wang in 2018 proposed spar-optimized decomposition of seismic data using non-zero curvature of the Gaussian beam and used the waveform function obtained by decomposition for sparse Gaussian beam migration. Liu et al. In 2019 developed data-driven controlled beam migration based on Gaussian beam by utilizing for the slowness information from source and receivers to migrate selected events. Liv et al. In 2019 developed optimized space-time Gaussian beam approach with dynamic parameter control for seismic depth imaging. Ching et al. In 2019 improved on pre-stack Gaussian beam depth migration by directly calculating the local plane wave decomposition and wave field continuation starting from rock topography. And lastly, Hugh et al. In 2020 developed a two-dimensional elastic imaging method using vector space-time Gaussian beam propagation operators. Moving on in discussing for the development in Gaussian beam migration algorithm, the early stage of Gaussian beam migration building blocks is developed throughout the 80s, with Popov suggesting for the wave field calculation. Chervany and Senchik developed the migration in both 2D and 3D models, and Kachalov and Popov provides the blueprint for the migration of the Gaussian beam. In 1990, Hill proposed for the complete Gaussian beam migration algorithm, which then supplies for the development of Gaussian beam migration in the next decades. Firstly, the Gaussian beam have been developed into multiple types of beam migration. For example, fast beam migration, Gaussian packet migration, focused Gaussian beam, fractional beam migration, and also control beam migration. We also find the mixture of migration methods such as slowness driven migration, through amplitude migration, and least square migration with the Gaussian beam. Hill commented on the Gaussian beam behavior that it is best to have the beams as narrow as possible over their propagation paths because Gaussian beam migration become inaccurate solution to the wave equation if the velocity changes quickly within a beam width. If it is too small, the beam quickly increase in width as they propagate. Later in 1992, Hale identified two main problems in Gaussian beam migration computation efficiency, which are first, complex value beam times and amplitudes are computed based on Cartesian coordinates. The solution for this issue is to locate the efficient closest point along the ray path using the Delaunay triangulation n times log n or circular method square root of n. Second, limiting computation to only within the region where beam amplitudes are significant. The solution for this issue is by decomposing the subsurface image into coarse grid of square cells to generate simple and efficient loops over determined coordinates. Chervany F. Senchik mentioned that the amplitude of each beam decreases exponentially with increasing distance from the ray along the parabolic wave equation, establishing the fundamental of Gaussian beam propagation. Using the Gaussian beam principle, Multiple beam migration techniques have been developed which further improve the migration image of the Gaussian beam-based data. In the work of true amplitude Gaussian beam migration done by Gray and Blaystein in 2009, the migrated sections show a decay in amplitudes with depth because of lateral translational symmetry of simple geometry is equivalent to short domain common image gathers for cross-correlation image condition. For the convolution image condition, the aperture truncation effects are more visible because of the relatively larger amplitudes produced at greater distance. By solving the complex econal equation based on Gaussian beam propagation, pseudo-slowness is introduced. Li et al. In 2011 discovered that in conventional Gaussian beam theory, it mentioned the restriction of the beam shape to be symmetric around the central ray. Therefore, it is impossible for Gaussian beam to capture one-sided anomaly. The updated econal calculation enables the dynamic ray tracing to fill neighboring medium by considering second derivative of the velocity in the direction perpendicular to the central ray. Adaptive focus beam migration is one of work proposed by Young et al. In 2015. This method adopts the single input trace imaging approach of classical Kirchhoff migration by replacing the Green's function by its proximate form in terms of the adaptive focus beam integral. Fresnel beam migration is another Gaussian beam-based migration technique developed by Huang et al. In 2015. The narrow and stable half-width of the Fresnel beam allows the reflection energy to concentrate in a reasonable range in the vicinity of the central ray. Hence, a lot of migration noise that caused by large beam half-width in Gaussian beam migration is reduced. Al-Khalifa in 1995 first to study the differences of migrated image produced between isotropic and anisotropic medium. His study concludes that in the case of isotropic media, the migrated image would experience depth error as the reflector is positioned at too great a depth because the stacking velocity exceeds the vertical root mean square velocity. Therefore, anisotropic media give a substantially better image of the reflector position than did the Gaussian beam migration that ignores anisotropy. In establishing the fundamental image for elastic-based Gaussian beam migration algorithm, Zhu et al. In 2007 has applied his algorithm to both isotropic and anisotropic medium. In isotropic media, the image shows a spurious pull-up of the flat bezel reflector beneath the dipping thrust sheet, and some defocusing effect can also be seen along the thrust sheet. In isotropic, the bezel reflector has been properly flattened. To summarize this technical review on Gaussian beam migration, three recommendations for the GBM way forward have been provided. First is to expand the migration method to four-dimensional analysis. As mentioned in the previous papers, a lot of the researchers have conducted the migration in either two-dimensional or three-dimensional seismic data, and some of them even apply the Gaussian beam migration in 2.5 dimensional. But until now, it is yet to see the result based on the 4D analysis of the Gaussian beam migration. With the Gaussian beam migration allowed to be propagated in circular motion, it is perhaps that the hyperspherical propagation of a Gaussian beam can solve for the 4D analysis problem. Second is to study on the phase behavior of the propagating Gaussian beam. It is as such that based on the previous studies, some of them are studying the Gaussian beam migration based on the true amplitude seismic data. And the ray behavior can be developed in the circular motion also. It is yet to study on the phase behavior of the complex situation, albeit there is a fundamental calculation is done on the Fourier transform. Correlate as it is works greatly with anisotropic rather than isotropic media. And the last recommendation in this paper is to develop ray signature wavelet in acoustic wave field to separate multiple from true reflection and further enhance the signal to noise ratio. Presented here is the list of reference used in this technical review. With that being said, we are arrived at the final slide of this technical review on Gaussian beam migration. Thank you.